Παιδιά, σας βγάλαμε από τα δωμάτια, όπως μπορείτε να δείτε. Έχετε, όπως είπαμε και πριν, μέχρι τις παρά 20 να ανεβάσετε τα θέματα. Αυτό δεν άλλαξε. Συνεννοηθείτε μεταξύ σας κάπως, τώρα που δεν είστε στο ίδιο δωμάτιο, πώς θα ενοποιήσετε το αρχείο, γιατί το θέλουμε σε ένα αρχείο PDF, όλες τις ασκήσεις δηλαδή σε ένα αρχείο. Παρά 25 ξεκινάει η ομιλία του κύριου Ηλιόπουλου, αλλά δεν σας επηρεάζει σας αυτό κάπως. Συνδέστε μετά.
Μέχρι και 4 δεν έχουμε, 5 και 4 δεν έχουμε σύνολο για τα θέματα.
Αρχίσαμε 1 και 4, η εξέταση ήταν 3ωρη, οπότε 4 και 20 είχαμε πει ότι ολοκληρώνεται η εξέταση.
Ποια είναι η ώρα που πρέπει να παραδώσουμε?
5 παρά 20.
Ευχαριστώ.
Πες όταν έχει ανοίξει. Καλησπέρα σας κύριοι και κυρίες. Καλώς ήρθατε στις ομιλίες του διαγωνισμού PLANCKS. Σας ευχόμαστε καλή επιτυχία στο διαγωνιστικό σκέλος και σε όλες τις ομάδες οι οποίες διαγωνιστήκατε το προηγούμενο τρίωρο σε θέματα φυσικής, τα οποία τέθηκαν από τους καθηγητές κύριο Καρακασίδη, κυρία Πρασά Βάια, κύριο Ζούπα Ανδρέα, από το Τμήματος Φυσικής του Πανεπιστημίου Θεσσαλίας για το διαγωνιστικό κομμάτι. Πολύ σύντομα θα ανακοινώσουμε τα αποτελέσματα της ελληνικής εθνικής ομάδας που θα εκπροσωπήσει τη χώρα μας στο διεθνή διαγωνισμό στο Πόρτο, μαζί με άλλες 50 εθνικές ομάδες στη τελική φάση του διαγωνισμού στις 6 με 8 Μαΐου. Σας ευχόμαστε όλους καλή επιτυχία και ελπίζουμε πολύ σύντομα να έχουμε και τα νέα σας και την αλληλεπίδραση μαζί σας. Θα θέλαμε να καλωσορίσουμε τον κύριο Γιάννη Ηλιόπουλο, που είναι ο πρώτος ομιλητής του διαγωνισμού μας. Ο καθηγητής κύριος Ηλιόπουλος είναι θεωρητικός φυσικός, έχει γεννηθεί στη Καλαμάτα το 1940, έλαβε δίπλωμα μηχανολόγου ηλεκτρολόγου από το Εθνικό Μετσόβιο Πολυτεχνείο το 1962 και συνέχισε στο τμήμα θεωρητικής φυσικής του Πανεπιστημίου Παρισίου, όπου ολοκλήρωσε και το DA του. Από το 1966 έως το 1968 αποτέλεσε υπότροφο στο Ευρωπαϊκό Κέντρο Πυρηνικών Ερευνών CERN. Το 1969 έως το 1971 εργάστηκε ως Research Associate στο Πανεπιστήμιο του Harvard. Το 1971 έως σήμερα είναι στο Εθνικό Κέντρο Ερευνών CNRS στη Γαλλία, ενώ το 1978 εκλέχθηκε διευθυντής ερευνών στο Εργαστήριο Θεωρητικής Φυσικής της École Normale Supérieure. Ήταν διευθυντής στο εργαστήριο από το 1991 έως το 1995 και συνέχισε το 1998 έως το 2002. Ο κύριος Ηλιόπουλος έχει βραβευτεί με πλήθος βραβείων και μεταλλίων που αφορούν τη θεωρητική φυσική, με βραβείο Λαγκεβάν το 1978, Ματεούτς το 1979, 1986 με το βραβείο Σακουράι, ενώ το 2007 βραβεύτηκε με βραβείο Ντιράκ από το ICTP στη Τεργέστη. Είναι εξαιρετική μεγάλη τιμή για το Φοιτητικό Σύλλογο Τμήματος Φυσικής του Πανεπιστημίου Θεσσαλίας να φιλοξενεί τον καθηγητή κύριο Ηλιόπουλο σε αυτή την εκδήλωση. Θέλουμε θερμά να ευχαριστήσουμε εκ μέρους όλων των φοιτητών την παρουσία του στην εκδήλωση μας και την αποδοχή της πρόσκλησής μας για ομιλία, έστω και εξ αποστάσεως λόγω των συνθηκών, σε όλους τους φοιτητές φυσικής που συμμετέχουν από τα 8 τμήματα και σχολές που λειτουργούν στη χώρα μας σε αυτό το διήμερο διαγωνισμό. Είναι σπουδαία τιμή και σας ευχαριστούμε θερμά, κύριε Ηλιόπουλε, που παρευρίσκεστε μαζί μας σήμερα. Η ομιλία θα πραγματοποιηθεί για τεχνικούς λόγους στην αγγλική γλώσσα, οπότε μπορείτε να αναζητήσετε οι ομάδες και οι θεατές μέσω της πλατφόρμας του διάβλου στην περίληψη τη φόρμα για τις ερωτήσεις στο τέλος της ομιλίας. Η ομιλία θα διαρκέσει 90 λεπτά μαζί με χρόνο για τις ερωτήσεις, ενώ στη συνέχεια θα ακολουθήσει ένα quiz γνωριμίας από το σύλλογό μας, που οδηγίες θα σας δοθούν μετά το πέρας της ομιλίας. Σας ευχόμαστε μια πολύ ευχάριστη ομιλία. Μπορείτε να ζητήσετε την πλατφόρμα, όπως είπαμε, στο διάβλο ή στο προσωπικό σας email οι ομάδες. Σας ευχαριστούμε πάρα πολύ και ο λόγος του κύριο Ηλιόπουλο, τον οποίο ευχαριστούμε και πάλι θερμά που παρευρίσκεται στην ομιλία μας.
Εγώ ευχαριστώ, παιδιά, πολύ. Προσπαθώ τώρα να κανονίσω το... Μια στιγμή. Βλέπετε το... Ναι, μ' ακούτε?
Κύριε Ηλιόπουλε, δεν βλέπουμε ακόμα το share που έχετε κάνει.
Δεν ακούω, εγώ τώρα δεν σας ακούω.
Ναι, δεν βλέπουμε ακόμα την κοινοποίηση οθόνης που κάνατε.
Δεν το βλέπετε ακόμα. Λοιπόν, για να δοκιμάσουμε άλλη μια φορά. Να δούμε τι μπορεί να γίνει. Τι να κάνω, άραγε.
Χρειάζεται βοήθεια, μπορώ να σας βοηθήσω κάπου?
Αν μπορείτε, ναι. Δεν ξέρω, δεν θυμάμαι τι είχα κάνει. Τώρα δεν βλέπετε τίποτα.
Λοιπόν, θα πάτε δίπλα από το κόκκινο κουμπί.
Ναι, μα δίπλα εκεί κάνω, αλλά...
Πατήστε πάνω στο share
Ναι, το πατάω.
Οκ, και θα σας βγάλει στο κάτω μέρος desktop και window. Πατάτε στο desktop. Στο screen 1 που θα σας βγάζει. Screen θα σας βγάζει.
Αλλά στο screen 1 δεν δείχνει αυτό.
Οκ, μια χαρά.
Εδώ βλέπετε τίποτα.
Τέλεια, κάντε το full screen αυτό. Πατήστε το κίτρινο κουμπάκι.
Τέλεια.
Από το κόκκινο.
Όχι
Όχι εκεί.
Τώρα το βλέπετε.
Οκ, μια χαρά, ναι.
Πολύ ωραία. Λοιπόν, ευχαριστώ πάρα πολύ και μπορούμε να ξεκινήσουμε. Sorry, I forgot. I'm afraid I have to speak in English, right? Μπρος.
Οκ.
Μ' ακούτε?
Ναι, σας ακούμε μια χαρά.
Εντάξει. So, I continue in English, right? So, the subject is physics and geometry, or a different subject, a different title would be the concept of space in microscopic physics. So, what I want to tell you today is a very profound change that occurred the last, say, 40 to 50 years in our understanding of the, say, the concept of space. What is space in physics? And it's a story that is still going on. We have not yet finished the story, so it will be still work for you to continue and complete. I remind to the Greek audience that in Platon's Academy, it was written "Midisa geometritos isito mitithira," which means "Let no one ignorant of geometry enter my door." So this will be the story that I'm going to tell you. So I will talk about microscopic physics, which is the physics of elementary particles. So first question is, what is an elementary particle? Or different way, what is the world made of? So the world is made out of constituents, microscopic constituents of matter. And over the last century, we have uncovered many layers of this cosmic onion. We started with atoms, then we discovered that atoms were made out of nuclei and electrons, and then the nuclei were made out of protons and neutrons, and finally the protons and the neutrons were made out of quarks. There is no reason to believe that there exists such a thing as an innermost layer, and even less that we have already reached it. So tomorrow we may discover that what we consider today as elementary may not be elementary, may be bound states of other more elementary objects. The second, so this was the first ingredient, the constituents of matter is the first ingredient of the structure of matter. But then we have a different, for the moment, at least it seems to be different. Maybe tomorrow we will discover that it's the same thing. But for the moment, we believe it is different, which is what we call the quanta of radiation. It's like the photon. They are particles that transmit the interactions. So they transmit the interactions among the elementary constituents. We know that all interactions are mediated by the exchange of such quanta. The range of every interaction depends on the mass of the corresponding quantum. And you know the famous formula first written down by, in fact, it was written down earlier, but anyway, it's called the Yukawa potential, which tells you that if the mass of the exchange particle is m, then the potential is e to the minus mr over r. You see that when m goes to 0, you recover the 1 over r potential Coulomb or gravitational. Now, these are the constituents of matter, and they interact among themselves for the moment, we believe that there are 4 fundamental interactions. I try to be very careful in these things, in the sense that tomorrow things may change. This is an ongoing field of research, and nothing is definite. For example, just to give you an example, when I was studying physics, quarks did not exist. Nobody had seen quarks. So what I was learning was that the elementary particles are the proton, the neutron, etc. So later we understood that protons and neutrons are not elementary, they are made out of quarks. So tomorrow we may learn something else. So the 4 fundamental interactions are the strong interactions, which are responsible for nuclear structure. We call them strong. They must be very strong because they must overcome the electrostatic repulsion among protons. So in order to keep protons close together inside the nuclei, you must have forces that are stronger than the electrostatic repulsion. Then you have the electromagnetic interactions, which you know what they are. They are responsible for atomic and molecular structure. The weak interactions, they are responsible for nuclear beta decay, as well as the decays of other unstable particles. And finally, the gravitational interactions, which you all know what they are. This is the table of elementary particles. The quanta of radiation, for the strong interactions, we have 8 particles that we call gluons. In English, glue is things that glue things together, so it's the particles that keep together the quarks inside protons and neutrons. The electromagnetic interactions, the quantum of radiation is the photon. The weak interactions, which are mediated by 3 bosons, W plus, W minus, and Z0, and the gravitational interactions, which presumably are mediated by something called graviton. And then the matter particles, which are the quarks, as I said here, and the corresponding leptons, which are charged leptons and neutron leptons, electrons and neutrino, mu, etc. Finally, there is a final particle which has been discovered quite recently. It's called the Brout-Engler-Higgs boson, and it plays a very fundamental role in the structure of the world, but I will not have the occasion to talk much about it today. So this table shows our present ideas on the structure of matter. Quarks, now just to give you, to make precision here, quarks and gluons do not exist as free particles. They always are bound inside protons, neutrons, etc. And the graviton has not yet been discovered. We believe it is there, but we have not been able to discover it yet. Remarks. All interactions are produced, as I said, by the exchange of virtual quanta. For the strong electromagnetic and weak interactions, they are vector spin-1 fields, while the graviton is assumed to be a tensor spin-2 field. I say it's assumed because it has not been discovered yet. The constituents of matter have all spin-1/2. They are spin-1/2 particles. Don't ask me why, it's an experimental fact. They are divided into quarks, which are subject to the strong interactions, we call them hadrons, and leptons, which have no strong interactions. Those of you who know Greek don't need to be told what hadron and lepton means. Each quark species appears under 3 forms, often called colors, no relation with the ordinary sense of the word. Quarks and gluons do not appear as free particles, as I said before. Why? We don't know. It's again another experimental fact. In fact, this is a famous problem. Whoever solves this problem, whoever succeeds in proving theoretically that quarks and gluons, subject to the forces I said before should be confined inside the hadrons will get $1 million. This is one of the problems that the Clay Mathematics Institute has announced 21 years ago in 2000 exactly as problem of the century, and has put down $1 million for whoever solves it. So if any of you solves it, will become millionaire. Quarks and leptons seem to fall into three distinct groups or families, is what I said before. You remember here you have first family, second family, third family. You have quarks here and leptons there. Now, why they are three, we have no idea. Again, another experimental fact. And the sum of all electric charges inside any family is equal to 0. This we understand why, but I will not talk about that today. So, what I said before, when I said that there was a remarkable progress made in the last 50 years, this yielded into something that we call the construction of the standard model. It's a remarkable achievement of the last 50 years, and we succeeded in building a model, a theory, which describes accurately the strong, the electromagnetic, and the weak interactions. And so I will talk mostly about this model in this talk. It is based on two fundamental principles. First of all, it's a dynamical theory, which is a quantum field theory. I will explain what quantum field theory means in a moment. And the second ingredient has a property of symmetry, which is, we call it a gauge symmetry. Again, the word gauge, the term is not, it's an unfortunate term, but has remained now in the literature. This is what brings geometry into physics, and I will try to explain that. So first with the dynamics. Let me say that if you have questions, you could ask them during the talk. I will stop from time to time and ask if there are questions. This will help, presumably, if the logistics is proper, it will help to understand the rest. So I continue, and in a moment I will stop and ask for questions. So the dynamics. You know the two classical forces, electromagnetism and gravitation, right? They are both described by the same classical potential. It's a potential 1 over r. Both the Newton potential and Coulomb potential are 1 over r. And you don't have to think very deeply to realize that this potential is singular when r goes to 0. Which means that this is not just a mathematical curiosity, it has an obvious physical consequence. A classical atom is unstable. When Rutherford proposed this model for the atom, that there was a nucleus and the electrons were turning around, it was obvious that this did not make sense, because a charge like an electron turning around a center will radiate electromagnetic radiation and eventually will fall into the center, right? So this is what we said, that the potential is unbounded from below. It can go deep as you want. This was, in fact, the origin of Bohr's quantization rules, etc., which gave rise to quantum mechanics. Now, non-relativistic quantum mechanics solves this problem, and it solves it in a very strange way. As you know, non-relativistic quantum mechanics satisfies the kind of uncertainty relation, which is the delta x, delta p, the uncertainty on the position of the particle times the uncertainty on the momentum of the particle should always be larger or equal to h bar over 2. Now, which means that really the electron cannot go, that's what we say at least, cannot go all the way down to the origin, because then delta x will become arbitrarily small. And because of this relation, delta p will tend to become arbitrarily large. So anyway, whether you like this argument or not, you know that if you solve Schrödinger's equation, you will find that the Coulomb potential has a ground state. So the hydrogen atom has a minimum energy state, and there is no state with energy lower than that. So the energy is bounded from below, although classically it is not bounded from below. Quantum mechanically it is. But this is the non-relativistic quantum mechanics. If you try to take into account relativistic corrections, you will find that the problem reappears. Now a remark. A simple exercise is to try to solve Schrödinger's equation with a potential which is not 1 over r, but say 1 over r to the cube, something much more singular than 1 over r. Well, you will find that even with quantum mechanics, the potential 1 over r to the cube has no ground state. The energy is unbounded from below. So the uncertainty relations we said before do not solve the problem of the 1 over r potential, but not for every potential, only for the 1 over r potential. If you make it more singular, then the problem reappears. So I promised to tell you what's quantum field theory. Let me try to give it here, to tell you here. Start from classical mechanics in the upper left part corner of the slide. Classical mechanics of, say, one particle is defined by, say, the position of the particle and the momentum of the particle, two conjugate variables, which I call Q of t and P of t. And the problem of classical mechanics is to determine these functions Q and P as functions of t. Once you know them, you know their values at a given time, initial time, t0. Now, it's easy to go from classical mechanics to quantum mechanics. The rule is simple. You just decide by decree that Q and P are no more functions of t, but operator-valued distributions, in fact, but it doesn't matter. Let's say operators Q and operator P, and at equal times, they satisfy this commutation relation. Once you assume this commutation relation, you obtain quantum mechanics. So this is I call it the quantization rule. You start from classical mechanics, and then you have a well-defined rule that tells you how to obtain quantum mechanics. Now, I did that for 1 degree of freedom, 1 Q and 1 P. Nothing prevents you from doing the same thing with n degree of degrees of freedom. Q sub I of t and P sub I of t, I take in values 1 to n. Then the commutation relation becomes, it's exactly the same, and you have a Kronecker delta ij here, right? So this is the rule for n degrees of freedom. Now, for example, to give you an example of, well, this n may be n particles if you want, but you can also view them in a different way. Suppose that you consider that space is a lattice. Instead of having, you replace the continuum of space with a discrete lattice. And then at every point in the lattice, you have one variable q. So the index I here denotes the site of the lattice. So one way to take the limit for very large n is to take the number of points to infinity and simultaneously take the lattice space into 0. Then you obtain this I now will take continuous values, which I will call x. This x here is really the index I, it's nothing else, right? So when you do that, classically you obtain a classical field theory. For example, Maxwell's theory is of that kind, right? The electric and magnetic fields at a given point x as function of t could be, modulo some difficulties, could be considered as the dynamical variables of a classical field theory. Now again, the same rule will bring you from a classical field theory to the quantum field theory. Now you replace this commutation relation with this one. The only difference is that the Kronecker delta will be replaced by a Dirac delta function. So this is what I will call a quantum field theory, is the quantum version of the classical field theory. So the same way, what is classical field theory? Classical field theory is classical mechanics with an infinite number of degrees of freedom. So the same way, quantum field theory is quantum mechanics with an infinite number of degrees of freedom. It's not another quantum mechanics, it's the same quantum mechanics you have learned, but imagine that you have an infinite number of particles, if you want, or degrees of freedom in general. Right? So it's not another quantum mechanics. It's the same quantum mechanics you have learned in undergraduate courses. I don't know if I can stop here and ask for questions. Is it possible to have questions in the middle or not? Hello? Do you hear me?
Yes, very good.
Yeah. Is it possible to have questions now, or we better continue and have them at the end?
I don't see that any one of the participants have a question right now.
So, okay, we'll continue. Remark, if you have a relativistic theory, you always have an infinite number of degrees of freedom. You cannot have a relativistic theory with a finite number of degrees of freedom. And the reason is simple. In non-relativistic classical mechanics, you have, if you consider, say, collisions among particles, you have separate conservation for energy, momentum, and mass. If I take two pieces of brick and I smash them together, and then I gather all the pieces that I can find around, if I weigh them before and after the collision, I find the same mass. Mass has not been created by the collision. But if you are in a relativistic theory, you know that you have this famous relation E equals mc squared. So if you have energy, you can create mass. In LHC, at CERN, a collision among two protons results in average of between something like 100 and 200 different particles. So you have a large number of particles produced as a result of the collision. So if you have a relativistic theory, you should always consider a system with an infinite number of degrees of freedom. Well, modern theoretical physics has a precise date of birth. It's June 2 to 4, 1947. It was the Shelter Island Conference. I will not tell you all the story about this. It's a very famous conference, as I said. But although, as I said, it's the birth of modern theoretical physics, the most important results that were announced in this conference were two experimental results. Willis Lamb from Columbia University measured what became known as the Lamb shift. It's a difference in two energy levels of the hydrogen atom, which, according to, say, Dirac theory, not the relativistic quantum mechanics, what people considered as the relativistic quantum mechanics of the time, should be degenerate. And he measured a difference which was of the order of 1,040 megahertz. And the second was the value of the anomalous, which became known as the anomalous magnetic moment of the electron, measured by Kupes, and which again was in disagreement with prevailing theory of Dirac theory. These experimental results gave birth to what became known as quantum electrodynamics, which was the first consistent quantum field theory. You see, the reason why it was complicated comes from here. If you look at this commutation relation, it tells you that this is a delta function, a Dirac delta function, and you know that this is not a function, is what in mathematics we call a distribution, which means that this part is a distribution, this part also should be a distribution. So these are not operator-valued functions, but operator-valued distributions from the mathematical point of view. And as you know, distributions have very special properties. In particular, you are not allowed to multiply two distributions together. This created a huge problem for quantum field theory, which was solved essentially in 47, say between 47 and 48 by Feynman, Schwinger, Tomonaga, and Dyson. And this gave birth to quantum electrodynamics. It was the first successful quantum field theory. Now, why this solved these problems of the 1/r potential, if you want? Well, quantum field theories satisfy also uncertainty relations. Since they have commutation relations, you can also derive uncertainty relations. Quantum mechanics uncertainty relations, as we said, do not solve the problem of all potentials. The same way, quantum field theory uncertainty relations do not solve the problem for all quantum field theories. They solve the problem for a very small class of field theories, which we call renormalizable quantum field theories. I will not explain the origin of the term renormalizable. In fact, in our four-dimensional space-time, there exist 6 renormalizable quantum field theories. Don't pay too much attention on the notation I have here, but I will tell you what they mean. With phi to the cube, I mean 3 scalar fields interacting at the same point. Phi to the 4th, I mean 4 scalar fields interacting at the same point. Yukawa interaction, I mean a spinor field, 2 spinor fields, and a scalar field. QED, I mean spinor fields and a vector field. Scalar QED would be scalar fields and a vector field, and what we call the Young-Mills interaction, which is 3 and 4 vector fields. They are all the renormalizable interactions that exist. It's not that they are the ones we know. We know that there are no others. So this is a theorem. Only those 6 are renormalizable. Remarks. For many years, quantum electrodynamics, you see, quantum electrodynamics is one of them, is this one here. This is quantum electrodynamics. Is the spinor is the field of the electron, and this is the field of the photon. So for many years, quantum electrodynamics seemed to be the only interesting case. Today, we know that nature uses all 6 renormalizable interactions and only them as fundamental theories. It's remarkable because it started as just a technical problem. We know how to solve the singularity problem only for those 6 theories. And somehow nature knows it also and picked up only those theories, all of them. Not all 6 are used. What I call the standard model, it's a combination of all those 6 interactions. There is one problem, is the gravitational interaction is not one of them. If I try to write a quantum field theory for gravitation, I don't know how to do it. And nobody knows how to do it. That's again another open problem which will be left for you. Now, the uses of quantum field theory. It covers the entire domain of fundamental physics. High energy physics, nuclear structure, condensed matter physics, phase transitions and critical phenomena, cosmology and astrophysics. Everything, quantum field theory is the language of the world. It's not surprising because we know that quantum mechanics is the theory of the world, is the physics of the world, and quantum field theory is just relativistic quantum mechanics. So we know that the world obeys the theory, the principle of relativity and the principle of quantum mechanics. So the language, the mathematical language of physics is quantum field theory. Are there any questions up to here?
No, we don't have any questions.
Okay, so, well, let me make a remark. I don't know, since you don't have a question, there are 2 possible answers. Either that I am very clear or that I'm very obscure. It's one or the other, right? So hopefully, I hope it is the first, that you understand everything. But if you don't, please ask questions. Don't hesitate to ask questions. So now I will go to the second ingredient I mentioned, which is the symmetries, the symmetry properties. Now, what is a symmetry? It's a well-known but quite abstract concept. I will define it this way. Symmetry is an assumption, it's a physical assumption, which tells me that something, a certain quantity, has no physical meaning. Therefore, physically meaningful results cannot depend on it. Examples. I assume that the space around me is such that the position of the origin of the coordinate system is not a measurable quantity. Therefore, we can move the coordinate system. This means that I have invariance under translations. Same way about rotations. I assume, again, it's an assumption, that the directions of the axes in space have no physical meaning. Therefore, I can rotate the coordinate system. Therefore, I have invariance under rotations. Let me go a little bit in more detail into that. This is my space, it's a coordinate system. And take, for example, a free particle. Now, a free particle, by the dynamics, tells me that if it's free, its trajectory is a straight line. Invariance under translations means that if I take x prime equals x plus a, where a is a constant vector, no matter which one, but any constant vector, then I obtain the image of A of this trajectory is this one here, and invariance under translation tells you that if A is the trajectory of a free particle in the XYZ system, its image A prime is also a possible trajectory of a free particle. I can do the same argument for rotations, etc. Right? I will not do it here, but this is the essence of what I mean by a symmetry. Now, here's the first abstraction, which I will call internal symmetries. Now, here you have to be careful, pay attention. Now, we know this was more or less Heisenberg 1932. It's not really the argument as I put it here, it's more recent, it came later. But anyway, the first idea came from Heisenberg in 1932. So, we know that electrons have spin, and that the projection of the spin of the electron in an axis, no matter which one, can take two values, +1/2 and -1/2, right? So strictly speaking, we don't have one particle as electron, we have two. We have an electron with spin up and an electron with a spin down. So for a mathematician, we have two particles, not one particle, since there are two different orthogonal states in the Hilbert space of states. We physicists, we don't say we have two particles, we say we have one particle. Why? Because we know that our theories are invariant under rotations in ordinary space. So if I turn my coordinate system around, say, the x-axis, one of the x-axis, for example, then I will turn an electron with spin up to an electron with spin down. And since this operation of rotation is a symmetry of the theory, therefore nothing can depend on which orientation of the axis I took in the first place. Therefore I say that, well, it's the same state, just looked in a different coordinate system, right? So this was the initial remark. So Heisenberg noticed that in nuclei, a proton and a neutron play very similar roles. So a good approximation, if you change in a nucleus a proton with a neutron, you don't change much. You change a little bit because the protons are charged, the neutrons are not. But as far as nuclear level is concerned, the change is very small. So approximately, Heisenberg said, I can imagine that I have just one particle, which I will call the nucleon, which has a kind of spin, but it's not a spin like the spin of the electron. I will call it isospin. Heisenberg did not use these words. Anyway, today we call it isospin. So it is like a spin, but different, in a different space. And if the isospin is up, I will call it proton. If the isospin is down, I will call it neutron. And the same way that I have rotations in ordinary space that change an electron with spin up to an electron with spin down, I assume that I have also rotations in another space which is isomorphic to this one but is different, right? And then in a rotation I will change a proton to a neutron. So you see, for the first time in history, people considered transformations which do not change, which do not apply to the ordinary space in which we live. Symmetries that are different, we call them internal symmetries. They have nothing to do with the space-time point, x. They apply to a different space. Heisenberg's isospace is three-dimensional, isomorphic to our physical space. But the idea was, with the discovery of new internal symmetries, the idea was generalized to multidimensional internal spaces. The space of physics became an abstract mathematical concept with non-trivial geometrical and topological properties. Only a part of it, the three-dimensional Euclidean space, is directly accessible to our senses. You see, you have to think a little bit as a mathematician. If a mathematician wants to characterize a vector space, he has many ways of doing it, but one way would be to try to figure out all transformations that can apply to that space. So if I take this mathematical way of defining a space, you see that these isospin transformations, or whichever others I will have, are as good transformations as ordinary rotations, but they apply to a different space. Therefore, the space of physics is not only the three-dimensional plus time that we know, it's a multidimensional manifold, right, which may have complicated topological or geometrical properties. Then I go to a second abstraction, which in fact it was chronologically was earlier, was 1918. It's in fact between 1914 and 1918, when Einstein formulated the general theory of relativity, the general theory of relativity. Imagine the following stupid thing. You say, well, before I made translations, and I had x prime going into x plus a constant vector a, right? And then a straight line is mapped to a straight line. Now suppose that for just purely mathematical reasons, I decide to make translations that, however, the vector here with which I translate the point depends on the point, depends on x and t. So this point I translate this way, this point this way, this point that way, which means that this straight line is mapped now into a curve. Obviously, no free particle in its right minds will decide to follow this trajectory. If you want, so a double prime is this one here, is not a possible trajectory of a free particle. If you want this curve to be the trajectory of a particle, you have to introduce forces. You have to force the particle to follow this trajectory. Otherwise, if you let it alone, it will go straight like that, right? So, question, mathematical question. Are there forces for which a double prime is the trajectory? You see, a double prime is any curve you can think of which is generated by such a transformation, right? So, question, are there such forces? Well, I don't ask you to try to solve it because it's not an easy question, but we know the answer. So these are, I will call them local space translations. At every point, I'll translate differently. The question is purely geometrical without any obvious physical meaning. So we expect a mathematical answer with no interest for physics. Surprise. If you do that consistently, it's not easy. I don't ask you to do it. If you do it consistently, the dynamics which is invariant under local translations is precisely general relativity. The resulting force is gravity, one of the four fundamental forces. This is remarkable. I asked a purely abstract mathematical question. In fact, we would say a crazy question. Who wants to translate locally? Why? Right? But I asked the question, sit down, do the calculation, and I discover the forces of gravity. General relativity is the theory which describes the geometry of our four-dimensional space-time. On the other hand, as you know, because the variables in general relativity is the metric tensor of the space, right? So this is really a fantastic achievement, it was hard to understand. In the beginning, it was not understood that way. As I said, this was done by, Einstein followed the reason which was not precisely that one. In fact, this mathematical reasoning was more due to Hilbert. But anyway, this was the story of general relativity. So what happens, however, is the gravitational forces are not the only ones which have such a geometrical origin. And I will give you another example. Take the example of the quantum mechanical phase. Take the Schrödinger equation, which describes the motion of a particle in a potential V. This is the equation you all know, right? First derivative with respect to time. This is the Hamiltonian, which is the kinetic energy and the potential energy on psi. And this you have to supplement, because it's a linear equation, you have to supplement it with a normalization condition, which is this one here. So these are the system of equations that describe the motion of a particle in a potential V. Now you see that they are both invariant under this one and this one, under the phase transformation of the wave function. So if I go take the wave function, multiply e to the I theta psi, x is, I write x, I don't want to have to write every time t and x space, so x now is four-dimensional, right? So if I change the phase of the wave function, you see that this one does not change because that's a linear equation and the phase disappears. And this one, it's not linear, but because it is the modulus square, the phase again will disappear. Right? So with a constant theta, this is, sorry, I made it one. With constant theta, this is a symmetry of the theory. In other words, it means that the phase of the wave function is not a physically measurable quantity. As you know, this, as we said before, this means that we have a symmetry, and it's, since the symmetry is a continuous symmetry, I can take theta any value. This means that I have a conserved current, and this is a very important thing because the conservation of this current, of the conserved current, is precisely the conservation of the probability current. It is this conservation that allows the interpretation of this equation as a probability equation, as something which is the amplitude, the probability amplitude to find the particle somewhere. And as you know, probabilities must satisfy a conservation equation. And this is precisely the invariance under this phase transformation which brings this conservation of the current, of the probability current. Now, suppose now, so far so good, we know all that. Now suppose that you ask the question, the same question that we said before. What about changing the global transformation into a local one? Namely, what happens if instead of taking a constant theta, I take a theta which depends on x, arbitrary function of x? So can I promote the global U1 phase transformation into a local one? Namely, can I have a theory which is invariant when I change the phase of the wave function but the phase now is an arbitrary function of x and t? in a formal way, you see this invariance forms a group. And in mathematics, this is called the group of a phase. It's called U1. U means unitary, 1 means the number of dimensions. So a unitary number in one dimension is just a phase, right? So it's U1. Now, if I do that, if now I have theta becomes a theta of x, it means that I have a U1 factor, a group U1 at every point in space and time. Means that I promote this invariance from U1 to something like infinite times U1. At every point it's U1 cross U1 cross U1 cross U1, etc., an infinite number of times, right? Now, is it possible to do that? Well, I go back to Schrödinger equation. I try to put here everywhere e to the I theta of x, here and here. You see, the problem will come, this thing has nothing will happen to him, right? So the only problems will come with the derivative, because now if I apply the derivative, d mu means either time or space, right? So 0, 1, 2, 3, 0 in my notation, 0 will be time and 1, 2, 3 will be space. So if I take the derivative of e to the I theta of x, psi of x, I will get the term I want, namely the change of phase of the derivative, but I will get an extra term, which is the derivative of theta. This term is absent if theta is constant. So, which means that, as I wrote it before, this equation here, the Schrödinger equation, is not invariant under local phase transformations of the wave function. Right? The same way that Newton's theory was not invariant under local translations. So, same question. Can I change the theory in such a way as to restore the invariance? That is it possible to modify Schrödinger's equation in such a way as to obtain an equation invariant under local transformations? The first person who asked this question exactly was Vladimir Fock in 1926. It's remarkable because Schrödinger published his equation in 1926, and 2 months later, Fock published the calculations that the computation I will show in a moment. Again, the question is purely geometrical. Now, instead of being geometrical in ordinary space, it is geometrical in this simple space with just a circle, right? It's a one-dimensional space, but not a straight line, it's a circle, it's the phase, right? So purely geometrical with no obvious physical meaning. So, but this is something you know how to solve. And you have solved it, in fact, several times in your undergraduate courses. So, in fact, we can answer this question in 2 ways, as a physicist or as a mathematician. And I will try to do it in both ways because it's instructive to have it in both ways. So, as a physicist, as we know, so the physicist knows what has to do. He has to introduce a vector field A mu of x, such that every time you change the phase of the wave function with theta of x, you simultaneously change this vector field A mu minus 1 over E, this is just a constant, d mu theta. And then you replace the ordinary derivative with something which I will call the covariant derivative, something which is defined as d mu minus E, I, E is this constant here, A mu of x. Now, it's an easy exercise, which you can check, that this again, a linear differential operator, right? So you can use this operator instead of derivative in the Schrödinger equation, right? It's just another different linear differential operator. So it's easy to check that now d mu e to the I theta of x psi of x equals exactly e to the iota of x d mu psi. That means the derivative operator commutes with the phase. You can take the phase out, because precisely the extra term you get from him, which is the derivative of delta, cancels the term which will come from him. Right? Okay, so this is something you know. It is you have done it in under various ways and names already, both in classical electrodynamic theory and in quantum mechanics. So what it means here really is replacing d mu by d mu. If you take any theory, the Schrödinger's equation, and you replace the ordinary derivative by the covariant derivative, turns any equation which was invariant under the global phase transformation into one invariant under the local transformation, and from now on I will call local transformations gauge transformations. If you are interested in the origin of the name, I will tell you later. It's not at the end, it's not interesting. Okay. So, now, suppose that I do that. I take the Schrödinger equation and I replace everywhere the covariant derivatives. So you know what happens. Go back to Schrödinger equation. Replace everywhere the derivative with the covariant derivative. You know what will happen. Here this one will give you an extra term which will be proportional, because it's time. It will be the zero component of the field A mu, you know, A0, which is the scalar potential, the Coulomb potential, and this will give you the vector potential. So what happens is that the original Schrödinger equation is replaced by the same equation in the presence of an additional external electromagnetic field. So again, this miracle that we said before, right? We asked a purely geometrical question with no particular physical meaning, at least no obvious physical meaning, and we discovered one of the known forces of nature. Well, in order to obtain the full interaction theory, we must add the energy of the new vector field. And it turns out, if you work out a little bit, that it is this expression that you know. I will come back to this expression in a moment. So the resulting interaction is the interaction of a charged particle with the electromagnetic field. It's quantum electrodynamics. Again, it's not just gravitation. Also, quantum electrodynamics has exactly the same property. It has a dynamical geometrical origin. Something we do not understand very well. Why this purely geometrical question brought one of the forces of nature. Now, to understand a little bit better, let us see what a mathematician would have said. For that, suppose that you have a friend who is a mathematician, and you ask him this question. Well, the natural mathematical language for theories invariant under gauge transformations is differential geometry. I don't know if you have now, those of you who have already had a good course on differential geometry can skip the rest of the talk because they will know everything. But I will talk for the benefit of those who have not had such a good course in mathematics or differential geometry. Now, what is the think as a mathematician now for the moment? You try, you have your friend, you explain to him, I have this thing. Now he will throw away all the physics parts that you tell him and he will try to concentrate on the formal aspects of the equations. So he said, well, you have somewhere a space, because your wave functions or fields or whatever are functions of the space-time point x. So somewhere you must have a space which is the space-time and for us physicists, is the four-dimensional Minkowski space, which I will call M4. In general, the mathematician may say, well, let us make it even more general. Take any differentiable manifold M. Now, if X is a point in M, a field, which I will call phi index A of X, A takes any, so let's say, R values, right, is an R component complex valued function of X, which, in other words, it's a mapping of the manifold M on the complex numbers R times, right? Because I decided I have R fields at every point X. Right? So let's assume that phi A, for example, which is an R component field, belong to an R-dimensional linear representation, not necessarily reducible, of a compact Lie group G. What does it mean? It means that if I want to generalize the phase transformation I had before into a transformation that acts on a multi-component object, not just one wave function, but say R wave functions. So it will be a matrix, a linear transformation, a matrix R by R.
Κύριε Ηλιόπουλε, we cannot hear you right now.
You hear me?
Yes, now yes.
Okay, so I was moving a little bit behind my computer. So I will repeat. Now, as I said, I just want to generalize the phase transformation I had before. The phase transformation was kind of trivial. It was of the group U1, which from the mathematical point of view is trivial. It's just one transformation. So I want to make it more complicated. So suppose that I have R components, my wave function has R components, and then I make a transformation, a phase transformation, which also mixes the components. So I write it this way. So this is a kind of R by R matrix, which applies on the vector phi. Okay? Now, if this, I generalize, suppose that my group is not just U1 to the R, that means this is not, I just change the phase of each component, but as I said, I mix also the components, which means that my group G has P generators. In other words, I can make P independent rotations. Take, for example, if I am three-dimensional space, I can make 3 independent rotations. If I'm in a 2-dimensional space, I can make only 1 rotation. If I am in a 4-dimensional space, I can make 6 rotations, etc. So this P is the number of independent rotations I can make, right? Theta I are the parameters, and the T are matrices, numerical matrices, right? So, in mathematics, we call P the dimension of the Lie algebra of G. And Ti are P R by R Hermitian matrices. I will call global transformations the ones in which these parameters theta I are constants. And I will call them local or gauge transformations if they depend on X. So, I can continue this abstract mathematical language, but as I say, unless you know something about differential geometry, it will be hard to follow. So let me try to make it simpler. Now, what is the image you have? You have imagined that, take that this M, this base space I have M, is just a one-dimensional space, just one line, right? So, and you have just one field. So all this is just a 2-dimensional space, right? You have the horizontal axis will be M, and the vertical axis will be phi. So for every point in M, you find the value for phi, right? Okay, so every point in M, you can imagine a whole line in which there are the possible values of phi. A transformation of phi means that you move along this line. A transformation means that you change the value of phi to a different value of phi, but you don't change x, therefore you move along this line. A global transformation means that no matter which point of x you look at phi, you move all the phi's the same way. And the local transformation means that you move them a different way. Now, if you had asked your friend mathematician, he would have immediately told you that it's stupid to consider only global transformations because they are trivial. Everything moves and changes the same way, and you obtain a much richer geometrical structure if you move them differently. So I will try to explain that, but instead of doing it using the mathematics language, I will try to get a simplified version, which is lattice field theory. It means that instead of having I said before, for M I take a one-dimensional space. Let's make it even simpler. I take just a set of points, discrete, finite set of points. So I change M to some L, which is a finite set of points. So now instead of having a space down, I have points, and at every point I have this line of phi, right? So that's what for example, let me assume, since I am in 4 dimensions, let me assume that I have, I make discrete every axis, every dimension in 4, so I have a hypercubic lattice, right? The point x becomes now n times a is the lattice spacing, right? And the n is some 4 vector with integer components, which go from 0 to some number and mu. And mu is the number of points of our lattice in the direction mu. Right? The total number of points, which is the volume of the system, is given by the product of all n mu's. So this is my lattice. Dictionary between continuum and discrete lattice. A field phi, which is a function of x, becomes field phi sub n. N now labels the site of the lattice, the point in the lattice, and takes discrete values. Say a product of two, say took a phi dagger, if it is a complex field times phi, it will be just the product. If it's at the same point x, it will be just the product of at the same point in the lattice. The only thing which requires some care is when you have a derivative, because the derivative will contain the difference from n to n plus mu, where mu is the unit vector in the direction mu, d mu here. So it is the difference between the value of phi at the point n minus the value of phi at the neighboring point, but in the direction mu. So you have 4 derivatives, which is d0, d1, d2, d3, right? Now, the kinetic energy of my phi, which contains the derivatives, like you remember in the Schrödinger equation, will have terms that have phi dagger at the point n and phi dagger and phi at the point n plus mu. So if I take a gauge transformation, which is e to the I theta of x, phi of x, it will become now e to the I theta sub n, phi sub n. And you see that local terms like this one remain invariant, but terms involved with derivatives do not. because this term here, right? If I have phi n minus phi, if I take that square, I will have somewhere the term phi sub n times dagger times phi n plus mu. And then this one will pick up a term e to the minus I theta sub n, but this one will have an e to the I theta n plus mu. Phi n. So these do not cancel. So the derivative terms are not invariant. I knew that. This was what I had found already in the Schrödinger equation, right? That the derivative terms had to be changed and introduce the covariant derivative. So let me do that. In order to restore invariance, we must introduce a new field which carries both indices n and n plus mu. I will call it this way. And they decide that satisfies these properties here. The Hermitian adjoint of this field is the u to the minus 1. It's a unitary field. So, under a gauge transformation, I will decide that it transforms this way. From the left with e to the I theta sub n, and from the right with e to the minus I theta n plus mu. So U are R by R matrices, right? Which can be parameterized, as I had before, the same way, right? Now, we modify the kinetic energy term and replace it. The terms that were n and n plus mu, I make them n, u, n plus mu. Now, u has two indices, n and n plus mu, therefore it goes between that and that. In the continuum limit, when a goes to 0 and n goes to infinity, the a's I have here will become the fields I had before, the gauge fields I had before, the same like the photon I had before. So you see now the important geometrical property. Fields, ordinary fields like phi, live on lattice sites. Phi have just one index n. But gauge fields, like A's here, have two indices, n and n plus mu, therefore they live on oriented lattice links. Mathematicians are right because they do not we call them fields, photon fields or something. Mathematicians don't like that. Mathematicians call them connections. Because really that's what they are doing. They connect the point n to the nearest neighbor n plus mu. And you need such a connection because precisely you decided to have local transformations and you have derivative operators. Derivatives really involve two neighboring points. To finish the story, you have again to compute what I had, the f mu nu square that I had before, d, etc. Now, again, you can do it in two ways, as a physicist or as a mathematician. As a physicist, in fact, it was what Mills did. In the first physicists who did this work were Young and Mills, and that's why we call them Young-Mills theories. And Mills once had told me that his job was to compute this thing by trial and error. He did not know how to do it, so he sat down and tried something and then tried something else, etc. A mathematician would have done it immediately because he knew the answer. And the mathematician will think of the following question. You want something which has derivatives, it's quadratic, and it is invariant under these transformations. Well, a mathematician knows that the answer is unique. There's only one quantity which has these properties, while physicists had to work out by trial and error to find out. And the mathematician thinks the following way. Let us take the example of a plane, the simplest space. So you know what is a parallel transport of a vector. You start from a point, and then you imagine a vector there, and then you parallel transport this vector along some line. For example, straight lines. Imagine that you bring it down to a certain point, then you turn around, and then you go back again. So you go along a triangle. Now, if you are in a space, in a flat space on a plane, you see immediately that if you do that, you end up coming exactly at the same vector. So the vectors are identical. Now imagine to do the same thing in the surface of a sphere. You start from the North Pole, you go down along, say, a major axis, a major circle, and you go to the equator. Now the vector, which was, say, tangent on the sphere on the North Pole, remains tangent on the sphere, but has turned around, and now it is perpendicular to the equator. Then you go for some time around the equator. The vector remains always perpendicular to the equator. And then you follow the other major circle and you go back. But now you see the vector has turned. It's not the same. When you go back, you find a vector that has an angle between the new vector and the old vector have an angle. And this is what we say, that the sphere, the surface of a sphere, is a curved space, while the surface of the plane is flat space. So this, for the mathematician, the curvature, there is something which defines the curvature of the manifold, and it's unique. And this is what you found going around with your parallel transport of the vector. So let us do that the same thing on the lattice. Consider 2 points on the lattice, N and M. I call the path P and M a sequence of oriented links which join continuously these 2 points. And P and M is, I define this P as the product of the U field I have along this. Now this is just a sequence of links, and as I said, in every link I have the field U, so the product of all those U's along the links. You see, and when I make a transformation, at every intermediate point, the 2 transformations cancel, one from the left and one from the right, and I'm left with the 2 points N and M, e to the I theta N, e to the minus I theta sub M. So if I have a closed path, so if N equals M, right, I go around it, I come back to the same point, and then I take the trace of that. This is a gauge invariant. I don't change. So this is the way I will take the simplest closed path. I will call a plaquette. In a 4-dimensional hypercubic lattice, the simplest closed path is just to go around the square. And I call this a plaquette. Right? So I take these plaquettes and we can show, this is not very difficult, you could even work out details and show it, that this particular expression is what I need the 4x trace of this f, where f is this expression here, which took time at Mills to compute because he could not figure out this extra term. For a mathematician, it's trivial because it is the fully antisymmetric. You knew there is only one fully antisymmetric term, which is the commutator of A mu and A nu. So this is, So this is the curvature of the manifold. So you see, we ended up having all sorts of geometrical properties which have now dynamical meaning, because this curvature of the which manifold, it is the field space. So if you look at the field space and you look at the curvature of the field space, this is the kinetic energy of the fields of, say, what I call them radiation, the fields that mediate the interactions. So the great progress of the last 50 years in our understanding of the fundamental forces was the realization that they all obey the principle of geometry. So I have to take various transformations and make them local, and I generate all the forces, the strong interactions, the electromagnetic interactions, the weak interactions, and the gravitational interactions. They all obey this principle, geometrical principle. Again, let no one ignorant of geometry enter my door. So this is the standard model. How long do I have? How long do I have? Hello?
I think you have half an hour more.
Okay, fine. So the standard model it describes in a unified framework the strong, the electromagnetic, and the weak interactions. It is based on a rather complicated gauge symmetry. You remember I told you I have some group G. Now the G of the standard model is U1 crosses U2 crosses U3. U1, as I said, is the group of the phase. SU2 is the group which is isomorphic to the group of 2 by 2 unitary matrices with a determinant equal to 1. And SU3 is the group of 3 by 3 unitary matrices with determinant equal to 1. Now it's sort of abstract group, but this turns out experimentally that it is the invariance group of the standard model. It can be, now, since we talk about the space, it can be implemented in an internal space with as many as 10 dimensions. So if you want this, if you want to find the flat space, which is real, like our three-dimensional space, Euclidean space, and contains this group as a subgroup, it turns out that it's O10. So it is the group of orthogonal matrices which apply on a 10-dimensional Euclidean space. Now, why is that? I don't know. It's an experimental fact. This was a more or less mathematical and theoretical talk, so since I'm a physicist and you are physicists, I want to say a little bit about experiments. So the standard model and experiment. The standard model, if you write them down completely, has 17 arbitrary parameters. They are related to masses and coupling constants. Like for electrodynamics, you have the mass of the electron and the charge of the electron. They are arbitrary parameters. Well, the standard model, since it describes a very large number of particles and interactions, it has 17 arbitrary parameters. All this should be determined experimentally, and they have all been measured experimentally. So now we know everything experimentally about the standard model, and we can compare its predictions with many, many experimental results. So we can compute things and try to measure them experimentally and compare the results. This is the model gives a very large number of predictions, and it has been enormously successful. I will show you some results. For example, here they are all sorts of measurable quantities which have been measured, have been computed by the theoretically, and these are the results. For example, this is the mass of what we call the Higgs boson. This is the mass of the W boson, of the width of W boson, the mass of the Z, etc., etc., etc. Right? All sorts of quantities that have been measured experimentally and can be computed in terms of the parameters of the standard model. This is the result. This, in fact, gives you what the experimentalists call the pool. That means how you have to pool this theory between the experiment to fit between theory and experiment. So 0 means perfect fit, 1 standard deviation, 2 standard deviation, etc. And you see, they are really fantastic things. There is one which is a very controversial thing. It's a very old result, an asymmetry, which is 2 standard deviations away, and that's the worst you can think. Everything else is fantastically measured. It's really the most impressive thing you have. This is another very impressive thing. This is the effective strength of the strong interactions as a function of the scale, of the energy scale in which you measure it. You can compute this change of in terms of the energy scale. This is the theoretical curve. The width of the curve is the theoretical uncertainty, and these are the experimental points. I mean, really a fantastic agreement between theory and experiment. And I can continue, it does not matter, this is another. These are the measured quantities, these are two quantities that are correlated, so these are the experimental uncertainties, and this is the theoretical result. This is the spectrum of the particles. You have the pion, the proton, the kaons, etc., etc. As you measure them experimentally, these are the masses in MeV, right? And as you compute them by a complicated scheme of lattice calculations of QCD lattice, every point here is hundreds of hours of supercomputing time, computer time, right? So it's really a fantastic effort, and you see that the agreement between theory and experiment is really remarkable. These are predictions of the standard model which have been verified experimentally. The first thing I choose to show you is the discovery of what people call the weak neutral currents. Gargamel was a huge bubble chamber. It's a detector, all-time detector. We don't use bubble chambers anymore in physics, but back in the 70s we were using them. And the reaction they would find was elastic scattering of neutrinos on electrons. In 1972, people believed that there were no such reactions. And the standard model said, no, we must have this reaction. And here it is. You see, the bubble chamber is, the good thing with a bubble chamber is that you can visualize the tracks left by the particles, charged particles. So the neutrino beam was coming from the right here, and then hit an electron here, and the electron moves. The neutrino you don't see because it's neutral, but you see the electron. It moves in the forward direction, and here it is. This is an electron. This is the trace of an electron. Very beautiful experiment in which really established these properties of the weak neutral currents. This is another beautiful experiment. This measures the cross-section, electron-positron annihilation to everything, hadrons. Well, it's normalized with the same thing in electron-positron goes to mu plus mu minus. And this is the theoretical curve. And these are the experimental results. You see the points here everywhere, the experimental results. Can you imagine, you can compute this curve theoretically and you measure it experimentally. A fantastic confirmation of your theory. necessary condition, as I said, for the consistency of the model is that the sum of the electric charges in every family is 0. So at the beginning, experimentalists discovered a third lepton, which was called tau lepton. These are charged particles. So immediately the theorists said, no, you must also have 2 quarks to compensate for this charge. And indeed, B and T quarks were discovered. In fact, the T quark, this is another beautiful experiment which discovered the W and Z bosons at CERN in 1983. They use this, what they call a Lego plot. It's like Lego. The reason, what they mean is that they measure the energy deposited in every part of their calorimeter. And you see this is a W in which you have 2 leptons and nothing else. And this is a Z, you have just 1 and nothing else. This is really a this is W, this is Z. Very beautiful experiments. You see energy deposited here and nowhere else. Energy deposited here and nowhere else. The discovery of the Higgs boson, this is the discovery. Now think of that. This is the background, goes like that, and theory tells you there will be a little bit an excess of events here, and here you find them. This is the same thing if you subtract the background. And similarly here for another decay mode. But this is the most impressive. Can you see that? You must be able to compute this background very accurately, and the theory tells you how to do it, because if you make a mistake in this computation of the background, you will lose the signal. So you must be able to compute, and then you observe this excess of events. Sorry. Well, these are just pictures of beautiful events of the from the CMS detector and of this Braut-Engler-Higgs scalar at CERN. It does matter. So, conclusions. The connection between physics and geometry has come to stay. It's not just a theoretical artifact. As I try to show, it is solidly anchored in very many and very detailed experimental results. So this is really the language, the new language of physics is geometry. Just to give you a historical thing, when I had your age, that's many, many years ago, we physicists had to learn group theory by ourselves, because until that time, physicists did not learn group theory. But it was the time when Gell-Mann discovered SU3, etc., so we had to learn group theory. Now the young generation have to learn geometry, in addition to group theory, right? So group theory and geometry. Geometry was developed in the last 50 years. Many questions remain unanswered. So there's still lots of work to be done, and this will be your job. Why this particular group? Why we have U1 crosses U2 crosses U3 and not something else? We don't know. A good theory must answer this question, and we have, which means that we don't yet have the good theory. What is the dynamical role of the internal space? I told about this. I said that there is the base space, which is the Minkowski space, and the dynamics really happens there because the transformations, the thetas, the angles, or whatever, depended on the point x. But also I told you that the real space for physics is a much larger one. It is the 4-dimensional and probably something like 10-dimensional. What happens to the points of these extra dimensions? why don't they appear as functions, as arguments in the transformations? We don't know that. There are theories like that. People very many years ago, just immediately after Einstein wrote the general theory of relativity, a guy by the name of Kaluza thought of the following thing. He said, well, in the general theory of at that time, the only forces that were known was gravitation and electromagnetism. Gravitation, by Einstein's theory, was the variable was this metric field, which called H mu nu. It's a 4x4 matrix, right? And gravitation and the electromagnetism had this vector potential A mu. So he said, imagine that I have a 5-dimensional space, not 4, and I do gravity in this 5-dimensional space. Now, in 5-dimensional space, the metric tensor will be 5 times 5 matrix, right? And now I assume that one of the dimensions of the x, the 5th dimension, becomes compact. It's not a dimension that goes from minus infinity to plus infinity, but it's a small circle. And it's so small that practically that nobody who lives in the 4-dimensional world can see it. Smaller than anything you can see, right? Now, it's easy to see that now you can split the 5x5 matrix, which is the tensor, the metric tensor in 5 dimensions, into a 4x4, and then you are left with a column and a row on the right and underneath, which precisely the 4 components there will be the 4 components of a vector field, and with the adjoints of the other side, and there will be also a scalar. So that means that gravity in 5 dimensions is seen from the point of view of a 4-dimensional observer as gravity plus electromagnetism. It's called the Kaluza-Klein theory. So is this the right way of doing? We don't know. Maybe these extra dimensions, if you want, are really space dimensions, like the ones we know, except that they are very small and compact. Take a simple example. A plane, a cylinder, and a sphere are all 2-dimensional surfaces, right? What's the difference? In a plane, the 2 dimensions, they all go from minus infinity to plus, they extend to infinity. They go from minus infinity to plus infinity. A cylinder, 1 dimension goes from plus infinity to minus infinity to plus infinity, but the other is a circle. It goes from 0 to pi. And in a sphere, both are compact. They go from 0 to pi. Which means that if an observer who's far away, which does have a very good resolution, will see the plane always correctly as a plane, but will think that the cylinder is a line. You won't be able to resolve the small circle around, and will think that the sphere is a point. So if you look from far away with better resolution, you may think that you may see fewer dimensions in your space. What we think we see as a 4-dimensional, as a 3-dimensional space, ordinary space, has in fact many more dimensions, but they are so small that we don't see them. It means that at every point in our 3-dimensional space, there may be a compact internal space. There are theories working in this direction, but for the moment we don't know. One of the problems of the standard model, I said, is that gravity is left out. Why? Because it's not one of the renormalizable theories, the 6 theories I mentioned before. So which means that since we have to, gravity exists, it's there, I mean, we see it. Since we have to include gravity, we must change the language we are using. Maybe the correct language is not quantum field theory. Maybe it's something else. What? Well, most theorists right now work on extended objects like string theories, but I will not talk about that. Well, you can think of many other questions like that. So, there must exist new physics beyond the standard model. The standard model does not answer all the questions that we want to ask. Again, conclusions. We're expecting new physics to be around the corner, but at the LHC we see no corner. For example, people were speculating that maybe the LHC with increase in resolution would try to discover these extra compact dimensions of space. It did not. We did not discover anything new there. So if anything happens, it must be at much higher energies. The easy answer is that we need more data at higher energies. The trouble is that there are 2 problems. We do not know what kind of data. If you ask me now, suppose that God would come in front of me now and say, if you ask me a question, I will give you the answer. I don't know what kind of question to ask. You can't ask as a question, give me the theory of the world. It has to be a specific question, right? So I don't know what is the right question to ask in order to make progress. The second big problem is that they will not come for quite a long time, this new data, because now we entered a period in which every step in experimental, resolution is a 30, 40-year job. So we won't have the answer before, say, 20, 30 years. It's a rather frustrating situation, especially for some of us. So my conclusions, and I will stop. We have a very successful theory, and we will leave the problem of its completion to the younger generation. It will be your job, young ladies and gentlemen. I will not learn the answer. Thank you.
Κύριε Ηλιόπουλε, έχουμε μια ερώτηση.
Πολλές, όσες θέλετε.
It's about our previous topic, about...
Sorry, yes?
About the previous topic, about the 6 interactionals
Yes.
that the nature uses.
Yes.
We talk that nature uses 6 interactions and it uses only them, right?
Yes.
Okay. How did we prove that these 6 exist? Did we prove them mathematically or with experiments? 2
independent things. The mathematical problem is to prove that they are the only ones which in a 4-dimensional space-time, they are mathematically consistent. And this, it's not a difficult proof, but first year, the level is first year graduate course. Any good quantum field theory course has this proof. Right, so it is a little bit above the undergraduate courses you have now, but it's not much above. So you can find that this proof in every good quantum field theory book. And it is really a kind of question of the way you prove it is that you find that every other theory is too divergent, contains divergences that cannot be taken care of by these uncertainty relations. The same way that you can prove very easily that only the 1/r potential has the good properties of having, say, energy bounded from below and wave function which is not singular to the origin and things like that. Well, the same way you can prove that only these 6 theories are in. Now, why they are the ones that nature has chosen, this is an experimental question. Because the model which uses all of them is in excellent agreement with the experimental data, as I tried to show to you.
So we actually proved these interactions also with examples, right? With experiments.
Said once more.
We prove these 6 interactions also with experiments, right?
Well, now we prove that, as I said, there are 2 independent questions.
Okay.
The first question is how many is mathematical. How many interactions are consistent, mathematically consistent in 4 dimensions? And this is 6. This is a mathematical theorem. You can prove that, right? Second question, does nature use all of them? Right? That's independent in some sense. We don't know why nature had the good idea of using the interactions which we can prove they are mathematically consistent. Nature could use something else. After all, gravitation is not among them, and nature uses. So, for particle physics, nature, experimentally now, we find with astonishment that nature uses all those 6 and nothing else. So as I say, it is just 2 independent questions.
Okay. We know more than these 6 that the nature doesn't use?
We have an infinity of, I can write an infinity. For example, I wrote 5 to the cube and 5 to the 4th. You could ask me, why don't you write 5 to the 76? I can write it, but mathematically it's not consistent.
Okay, thank you. Yorgos Liberis has also a question.
Yes.
Hello, sir. I would like to ask you, how do you think dark matter will fit in this framework?
Dark matter?
Yes. Do you think that we will need a new framework or?
Yes, it is one of the questions that we don't know the answer. Observationally, experimentally, if you want, well, I don't want to use experiment for cosmology or for astrophysics because it's a different observations. So observationally, we see that we need dark matter to explain the rotation curves of the galaxies and the galaxy formation and all that, right? So we know that in our universe, a large part of matter that exists in our universe is dark. Dark in the sense that does not interact with electromagnetic fields, so it does not rayonate. We cannot see it in any, it emits no electromagnetic radiation. In that sense, it's dark. So this is an experimental fact, an observational fact. What is it? That we don't know. We can have theories. We have many theories. But if there are new particles, for example, we must be able to produce them somewhere in our laboratories. And we have not succeeded to do so until now. So we don't have no idea what is this dark matter, although observationally, we see that it should be there. Did I answer your question?
Yes, thank you for your answer. It's an open problem. That's what I'm taking.
Yes, it is a problem for you.
Yes, but hello, that I get your answer.
Okay.
Nikolaos Ludis has also one question.
Yes, hello, thank you for your talk. Another question on the six field theories that you described.
Yes.
Two of them correspond to quantum electrodynamics, right?
Yeah, one for spinors and one for scalars.
Do the rest, the four left, do they correspond to...
Excuse me?
Do the four left, the other four, do they correspond to strong and weak forces, or
No.
we have to put them all together to...
Complicated. The strong interactions come from Young Mills, from SU3 Young Mills. It's the last one. The others, all the others, are in a combination of electromagnetic and weak. So the weak interactions, is part of them are Young Mills, are the ones that are mediated by W plus W minus and Z0. Electromagnetic, the ones that are mediated by the photon. And then the other four, whatever they are related to the Brout-Engler-Higgs boson. So they are the interactions in which the Higgs boson has with the quarks, the leptons, and the other particles. So it is, they all enter the standard model, but not on equal footing.
All right, thank you.
And we have also one more question, which is how far are we from a complete theory of everything, and how big part will the understanding of geometry will play?
Well, I can't answer you. See, somebody has said that it's the hardest thing is to make predictions, especially for the future. So it's very easy to make predictions for the past, but not for the future. First of all, I don't know if it makes sense to talk about the theory of everything. It may make sense, but this is not a really scientific question. You see, how can take the part of scientific research in, say, 2 centuries ago was the exploration of the surface of the Earth. So the big, great explorers, Livingstone, Stanley, all these people, were the ones who traveled to foreign lands and tried to see what happens there, what were the rivers, the mountains, the thing, because there was we did not know how distant lands were made. They were discovering new islands, new things. This was a great field of research, but it was by construction, by definition, was finite, because the surface of the Earth is a finite surface. So after some time, you know everything about the surface of the Earth. So by definition, in this field of research, you can have what I will call the theory of everything. You can have a map of the surface of the Earth, very detailed, everything. How do we know that our research in elementary particles is not also finite like that? Maybe one day we shall have the theory of everything, and then there will be nothing to look for. The only thing I can say is that for the moment, at least, we do not seem to go this way. Every time we answer a question, for example, with the standard model, this opens the way to even more questions. We do not seem to exhaust the problems. But of course, nobody knows what will happen much later.
I have a personal question too. Do you think that one day we will learn about everything?
Well, it's the same thing. What do you mean by everything? Most of my intuitive, you see, this is not a scientific question, it's more, say, metaphysical question. So my own personal feeling is the answer is no. There will be always new things to learn about. Well, you can argue there are some, because it depends what you mean by everything. Do you include in everything ourselves? We are part of the world, we are not outside the world, right? And you know that there are theorems, logical theorems, that says that no finite system can possibly describe fully itself. So that means that in some sense we will never know everything. But these are not, I'm not arguing this way. I say even if I exclude ourselves, still I don't believe we shall learn everything about, say, high energy physics, particle physics, because you can think of exploring shorter and shorter distances, say higher and higher energies, and I see no reason to believe that there will be the end of it, that I cannot go to higher energies. Why not? Why?
Thank you very much.
Welcome.
To everybody, feel free to make any questions. We have one more question from Professor Karakassidis.
Yes.
We cannot hear.
I can't hear anything.
We cannot either.
Listen to something?
Yes.
Okay. I would like to thank you very much for being here. It's not a question, but I'm professor in the Department of Physics in Lamia, University of Thessaly. I first have read your name in a book of Stefanos Trachanas, who was acknowledging you when I was a student and I was reading quantum mechanics. And then I think I had the opportunity to listen to a talk when I was in France with my PhD.
Sorry, I can't. The connection.
Okay.
Say it once more. I followed you until you talked about.
I would like to thank you very much for giving the talk to the students, both to our students and to the students, to other students.
I thank you very much.
And that you accepted the invitation from the students, which are, I would like also to congratulate them for this. And I really liked two things in your talk, if I can say this.
Yes.
The mathematics approach and the physics approach, which is really very important for the students, that they must think like physicists, but they must also think sometimes like mathematicians, because this can help very much. And the other thing is that you encourage them that there is work for them in the future.
Oh, yes.
And I wish you that you reach a time where you can see some of these results from these young students, and that we have the opportunity to listen to you again. And thank you again very much.
Thank you very much.
So from me is okay. So I don't have any other question to add. Thank you very much.
Thank you. So have a nice meeting, and my best wishes for great success.
We have one last question, Illiopoulos.
Yes.
Give me a moment, please. The question is, isn't it odd that not all the theories in physics are unite?
Excuse me, I didn't understand the question.
Isn't it odd that not all the theories in physics are unite? Shouldn't be unite.
You mean
in a kind?
You mean theories or theorists?
Theories.
Yeah. Oh, this is you mean why we have a different theory for gravitation, and is that what you mean?
Exactly. Are they in some way united?
It is. This is what I was. Let us see if I have it. Well, I lost it somewhere. I don't know. Anyway, it is what I said. Why this U1 crosses U2 crosses U3? You would expect to have just one theory with one single, possibly simple group, which will include everything. And we don't have that. So this is one of the great problems. We call it grand unified theories or things like that. There is a lot of work which has been done, and people continue to do it in that. But for the moment, we don't know the answer.
So it may be that in the future we find the way that all the theories are combined together.
This is the old dream of mankind, to have a unified theory where all phenomena are included, that you don't have to say, oh, this is gravitation, I take this theory, this is something else, I take the other theory. So in principle, that's what we dream of. But for the moment, it's still a dream.
Thank you very much, Herr Illiopoulos.
Thank you again.
Thank you, Dr. Illiopoulos. It's a great honor for us for being here giving this talk. So I will continue in Greek. Οπότε σας ευχαριστούμε πάρα πολύ που βρίσκεστε εδώ. Σας ευχαριστούμε πάρα πολύ για την ομιλία που δώσατε και ευχαριστούμε και τους συμμετέχοντες τόσο μέσω της πλατφόρμας Teams όσο και μέσω του Διάβλος για την παρακολούθηση της ημερίδας που πραγματοποιούμε. Είναι σπουδαία τιμή για το σύλλογό μας που βρίσκεστε εδώ, οπότε και πάλι θέλουμε να εκφράσουμε τις θερμές ευχαριστίες το συνόλου των φοιτητών. Σας ευχόμαστε τα καλύτερα, να είσαστε ασφαλείς και ευχαριστούμε πάρα πολύ που συμμετείχατε στην εκδήλωσή μας.
Εγώ σας ευχαριστώ πολύ και σας εύχομαι καλή επιτυχία, λαμπρή σταδιοδρομία σε όλους σας.
Σας ευχαριστούμε πάρα πολύ. Οπότε στους συμμετέχοντες θα υπάρξει ένα διάλειμμα μέχρι τις 7 και 10 και θα συνεχιστεί με ένα μικρό παιχνίδι quiz ανάμεσα στους φοιτητές φυσικής ανά τα τμήματα στην Ελλάδα. Οπότε θα σας αποσταλεί ειδικό email για το πώς, με κάποιες οδηγίες, και θα μπορέσετε να συμμετέσχετε στο ίδιο link είτε στο Διάβλο είτε στο Microsoft Teams στις 7 και 10.
Ευχαριστώ.